Hello friends, welcome to CEC Gurukul Live Lectures. Dear friends, today in this session we are once again going to talk in our series on mathematical methods for economics, and for the discussion we have with us in our studios Dr. Neeti Bhutani. Dr. Neeti Bhutani is Assistant Professor in Department of Economics and she is teaching in Hindu College University of Delhi. Dear friends, she is going to talk specifically on absolute values. In previous session also we discussed a lot, and today also we are going to cover a lot on absolute value. We are going to talk on properties and graphs. Friends, if you have any question while listening to us, feel free to talk to us through our toll-free number. Our number is 1800110430. Now, I would like to welcome our guest, Dr. Neeti Bhutani, once again. Hello, ma'am. Welcome to the lecture.
Thank you very much, Geetika. Hello, everyone, and a very warm welcome to all of you. Today, we will be talking some more about the concept of absolute value. In fact, if you have been following my lectures, I had earlier devoted one whole lecture to a discussion of this concept. I had given a geometric interpretation to the concept of absolute value in terms of distance, and we had also practiced a number of equations and inequalities. This was lecture 4 in the series, to be precise. In today's lecture, we will build some more on this, and in particular, there are two new aspects that I would like to talk about. First of all, I would like to talk about graphs of functions that have some algebraic expression contained within the absolute value symbol. Now that we have formally introduced graphs in our series, we've been talking about graphs since the previous lecture. Also, we've talked about linear functions. So I think the time is ripe to start taking a look at visuals relating to absolute values and absolute value functions. So this will be the first part. Secondly, I would like to talk about some very important properties of absolute values or absolute value functions. These are properties that you come across very often when you're doing various proofs in mathematics. So do pay attention when I walk you through these properties. So finally, once we're done talking about graphs and properties of absolute value functions, we will then see if we can have a discussion on this. If you like, you can call. Otherwise, this is what the plan is for today. But before I begin, let me do a quick recap of my fourth lecture. Let me tell you about the main points that I had covered in that lecture. So if you take a look at this slide, let us suppose we have a number x. It is let's suppose we have a real number x. Then the absolute value or the modulus of x, the absolute value is also known as a modulus of x, that is denoted by x with a vertical bar on each side of x. You can see where my cursor is pointing. So we write x with a vertical bar on each side, and that symbol then represents the absolute value or the mod of x. And in terms of the interpretation, we said, if you go back to that lecture, that the absolute value of x represents the distance between that number x and 0 on the number line. And because we gave it the interpretation of distance, and because distance can never be negative, therefore we have that the absolute value of x is always going to be non-negative. It's always going to be greater than or equal to 0 for all values of x. And in that sense, mathematically, we derived the expression, the mathematical expression for absolute value of x as follows. Absolute value of x is equal to x itself if the number x is non-negative or greater than or equal to 0, and the absolute value of x is equal to minus x if the number x is negative. So let us suppose that we have a function which is defined by f of x equal to the absolute value of x, where x belongs to the set of real numbers R. Now, this is an example of what we call an absolute value function. So, we can think of an absolute value function as a function that contains some algebraic expression. It has some algebraic expression which is which is contained within the absolute value symbol, which is contained within this these two vertical bars. So, at least one expression like that is there. So, that would make a function the absolute value function. However, for the moment, let's focus on what some books call the parent absolute value function, because ultimately it is this function mod of x which will lead to the other kinds of absolute value functions. So, this is something which we are going to delve into a little deeper. So, our function is f of x is equal to absolute value of x. And let us look at the graph of this function. So, let us start getting into visuals now. Now, if you remember what I told you in the previous lecture, a graph of a function f of x is a set of all points x comma y such that x belongs to the domain of the function d sub f and y is equal to f of x. So, we are going to plot all those ordered pairs x comma y such that x belongs to the domain of the function, and in this case our domain is the set of all real numbers, and y, the value that y will take will be the value determined by the function f of x. So, with this in mind, let us plot y is equal to absolute value of x. Excuse me. So, we want to plot a graph of y equal to x if x is greater than or equal to 0 and y equal to minus x if x is less than 0. Now, let us do things stepwise. Let us first look at the plot of y equal to x. Please take a look at this graph on slide number 4, and I would request that each graph be shown one by one. So, here you can see we've already discussed linear functions. So, we have a straight line here, and if you look at this equation of the straight line, this is an equation that where you have a straight line with a slope of 1, because you can see the coefficient of x is 1, and if I put x equal to 0, you can see y is going to be equal to 0. So, I have a straight line here whose slope is going to be 1, which is going to make a 45-degree angle with the x-axis, and this line will pass through 0, 0, the origin. And as you know that if you know the slope of a straight line and one point, that information is sufficient to draw the straight line passing through this point 0, 0. In any case, here it's a very simple graph. So, you know that if x is equal to 1, y is also going to be equal to 1. So, any point where the x and y coordinates are identical, all those points will be on this straight line y equal to, represented by y equal to x. And you can see here I have marked 1, 1, 2, 2, minus 1, 1, minus 3, minus 3. All these are points which I have already marked on this straight line. So, this is our graph of y equal to x in the general sense. Similarly, if we look at the graph of y equal to minus x, this is going to be a graph with a slope of minus 1. Please take a look at this graph, and here all points of the form x comma minus x. So, if x is equal to 1, then y is going to be equal to minus 1. If x is equal to 2, then y is going to be equal to minus 2. All these points will be on this line y equal to minus x, and here again this is we have information here that the slope of the line is minus 1, and this line will also pass through the origin, because when x is 0, y is going to be equal to 0. So, here also you can draw your line just on the basis of the slope and the fact that it passes through the origin. Right. So, this is a graph of y equal to minus x in a general sense. Now, we want to look at the graph of y equal to x when x is greater than or equal to 0. So, when x is greater than or equal to 0, so please take a look at this graph, this is important, then y is equal to x. Okay, so in that sense, we will, if you look at the graph of y equal to x, that will be this entire the dashed red line and the blue line parts of the line, both will be included. But because we want to include only that portion of the line which is corresponding to x non-negative, we will take only this blue portion of the line for y equal to x, because y is equal to x only if x is greater than or equal to 0. And we will not take into account this red dashed line. So what happens when x is negative? When x is negative, y is equal to minus x. So for the y equal to minus x line, we will only take that part of the graph which is corresponding to this blue portion here, because if we take the red portion of y equal to minus x, then we will have x positive or 0. So that's something which we don't want. We have already said that when x is greater than or equal to 0, then y is equal to x. So this is this is the first part of the graph, the blue part, and this is the second part of the graph. And combining the blue parts of both parts of the graph, we get this as the graph of the function absolute value of x. And you can see here that to the let me just get the arrows here. Yes. So to the right of x equal to 0, our line is given by y is equal to x, and to the left of x equal to 0, our line is given by y is equal to minus x. And this is our graph of the absolute value function given by mod of x. And you can get a better visual here with all the boxes. You can see here that whenever x is positive, so for example, x is equal to 3, then y is going to be equal to 3 also. Similarly, if x is equal to, let's say, minus 4, y is going to be equal to 4, and so on. So now our graph is given in this way. It's a V-shaped graph, and you can see that it is symmetric in the sense that if I were to fold this graph along the y-axis, then the two parts on the left of the y-axis and the right of the y-axis, they will overlap. Right. Let's take a look at another graph. Let's suppose our function is given by the absolute value of x minus 2. Now we know mathematically that the absolute value of x minus 2 is equal to x minus 2 itself if x is greater than or equal to 2, and it is equal to 2 minus x or minus of x minus 2 if x is less than 2. So again, if we plot these two lines separately, so if x is greater than or equal to 2, I follow the line y is equal to x minus 2, which is this green line on the right here. And if x is less than 2, I will follow the line given by y equal to 2 minus x, and that then will give me the graph of y equal to absolute value of x minus 2. Now, here there's another way of looking at things. You can also think of the graph of y equal to mod of x minus 2 as a graph which can be derived from this parent function, which is y equal to absolute value of x. So our original function here is given by this blue graph here, the blue V-shaped graph, which is y equal to absolute value of x. And what I am claiming is that the graph of mod of x minus 2 is nothing but a rightward shift of the original graph 2 units to the right. Now, this is something, shifts of graphs or translations, this is something that I will be talking about in another lecture. But since we are talking about a shift here, let me just give you some intuitive idea about a rightward shift, because that's the kind of shift we are talking about right now. Let's just think about why, because very often students have this issue that when you have a rightward shift, why do we put a minus after x and why not a plus? So let's just get an intuitive feel of what a rightward shift means, and let's just revisit this question in the following manner. So let us suppose I give you this graph of y equal to absolute value of x. Now this graph is sitting at the vertex of 0. So let us suppose I shift this entire graph in blue 2 units to the right, so that my new graph is given by the green line. So now just sort of forget that I was talking about the mod of x minus 2 graph. So I'm just saying, suppose I shift my original graph mod of x to the right, 2 units to the right, then what do you think the equation of this new graph will be? So that is what you have to talk about, you have to think about now. Now, the first thing notice here is that this new graph in green is having the same shape as the original graph, which is mod of x, except that it is shifted 2 units to the right. So we can think along the following lines. We can say that the new graph would have the equation y equal to mod of something. So we don't know, that's why I put a blank, I've just left this portion blank in between the 2 vertical bars. I'm claiming that this new graph would have the equation similar to a modulus, but we don't know what we'll put inside the modulus. So let's leave this portion blank for the time being. But we know that this will be the format. Now let's, with this as a base, let's look at a particular value of y. Let's suppose we take y equal to 0. Now, when y is equal to 0, if you look at the original graph, this graph in blue, y is equal to 0 when x is equal to 0, right? This graph is sitting on 0, 0. See where my cursor is pointing? Now, what about the new graph? The new graph will have y equal to 0 at x equal to 2. So, the question now is, when is y equal to 0 for the new graph? Now, we have to now decide what we'll put inside these vertical bars, such that when I take that the absolute value of that something inside these vertical bars, I should get a 0. And obviously, if I want a 0 as my y value, then that something inside the vertical bars should also be 0. Right? Now, if I put x equal to 2 inside the vertical bars, I'm not going to get a 0 because the absolute value of 2 is 2 itself. But if I subtract 2 from that 2, then what do I get? I get a 0, and the absolute value of 0 is a 0. So, my x value was 2, for which the value of y is 0, but that does not give me a y value of 0. So, if I take the mod of 2, so if I write x minus 2, look at this expression here inside the absolute value symbol, then I will get a 0. And again, you can check for any other value also. Let us suppose we take the value y equal to 2. Let's fix the value at y equal to 2. And you can see for the original graph, y is equal to 2 for both x equal to minus 2 and x equal to 2. But let's just focus on x equal to minus 2 for the time being. So we know that for the original graph, when x is equal to minus 2, the value of y is 2. But for the new graph, when x is equal to 0, then y is equal to 2. Now, clearly, if I take, if I just put x equal to 0, if I just put x inside the mod symbol, then I'll get x equal to 0, and then the outside y will also be 0. So, again, I'll have to subtract 2 from that 0 to, in order to get minus 2, and then the mod of that would be 2. So, that is why when x is 0, here we get for the new graph, mod of x minus 2 will become minus 2, and that then will give us a y value of 2. So, in this way, you can think about a rightward shift as one which will give us an equation which is y equal to the absolute value of x minus 2. Keep the value of y fixed and see what value associated with the new x will give you that same value of y, and in this case you will have to subtract a 2 every time. So, similarly, if let us say x equal to 2 in the original graph was giving you y equal to 2, and now it's x equal to 4. So, I'll have to subtract a 2 from that 4 in order to get a y value of 2. I hope this is clear, otherwise just think about it a little bit more. It's actually not that difficult. Right. Now, let's talk about some of the properties of absolute value functions, and please pay attention here. These are very important properties. In some books, these are given as properties of absolute value, but it doesn't matter whether we say absolute value or absolute value functions, because I could simply write that my f of x is equal to mod of x, and then just go ahead with the same analysis that I would do for an absolute value. So, either ways, we're basically talking about the same stuff. Right. So when I'm talking about properties, let's start. Okay, let's start with the first one. The first one is actually a definition which I had talked about even in my fourth lecture. Let us suppose we have two real numbers x and y. Right now we don't need y for the first part. By definition, we have that the absolute value of x is equal to the square root of x square, and that then is equal to x if x is greater than or equal to 0, and equal to minus x if x is negative. But the main part here is that by definition the absolute value of x is the positive square root of x square. Right. Now if we have two real numbers x and y, then the second property states that the absolute value of a product is a product of absolute values. So we have that if I take the product of two numbers x and y and then take the absolute value of the product of those two numbers, that is then equal to the product of the two individual absolute values, the product of mod x and mod y. Let us look at the proof for this. Now, by the first definition, you've seen here that the absolute value of x is equal to the square root of x square. So, instead of x, if my number now is xy, then the absolute value of xy by definition is equal to the positive square root, the square root here of xy, the whole square, right? Our number here is xy. So, this, that by definition is equal to the square root of xy, the whole square. Now this in turn I can open up, I can just take the squares separately. So this is equal to the square root of x square y square, which we can then separate into the square root of x square times the square root of y square, and that by definition is equal to the absolute value of x times the absolute value of y. So we have here that the absolute value of a product of two numbers is the product of the absolute values of those individual numbers. Let's look at the third property. Now here this is basically saying that if you take any number x lies between the minus of its absolute value and its absolute value. So to get a sense of things, let me give you an example. Let's suppose x is equal to 3. Then the absolute value of 3 will be 3 itself. So this right hand side of right part of the inequality would boil down to 3 is equal to 3. So that this original inequality is still satisfied. Now on the left part I'll now have minus 3 because mod of x is 3. So I have minus 3 which is strictly less than 3, and therefore this entire inequality is going to be satisfied. Similarly, let's say x is equal to minus 4. Now if x is equal to minus 4, then the mod of x will be 4, right? So the left part of the inequality now will become an equation because you'll have minus 4 here on the extreme left, which is equal to minus 4 because x is equal to minus 4, and that is going to be less than 4, strictly less than 4. So the idea here is that in fact what you should remember here from this property is this right part of the inequality, which is which comes in handy very often, that any number x is less than or equal to its absolute value. Look at this right part. So if x is positive, then x will be exactly equal. If x is non-negative, it will be exactly equal to the mod of x. But if x is negative, it will be strictly less than the mod of x. But in general, the number x, any number x, is always going to be less than or equal to its absolute value. So keep this in mind because this is a property which I'll be using when I derive when I do the proof of the triangle inequality, which I'm coming to in a bit. Okay, but before that, let's first look at the proof of this particular property. Now, typically when we talk of absolute values, we always separate things out into two cases. So here also we are taking two cases where x is either non-negative, it's greater than or equal to 0, or x is negative. Now let us suppose x is greater than or equal to 0. Please see now what I have on my slide here. If x is greater than or equal to 0, then the absolute value of x is going to be x itself, right, by definition. So the minus of the absolute value of x is going to be something less than or equal to 0, because the absolute value of x is going to be positive, greater than or equal to 0, and if I put a negative sign in front of it, that's going to be something which is less than or equal to 0. And because by assumption x is greater than or equal to 0, this second inequality follows from our assumption 0 is less than or equal to x, and because x is greater than or equal to 0, by definition x is going to be exactly equal to the absolute value of x. And you can see this is this entire result in the first in what is numbered number 1 as the inequality, that is matching with the original property that we are talking about. Now the second part, suppose x is negative. Now remember, when x is negative, the absolute value of x is going to be minus of x. So when I take minus of the absolute value of x, that will become x, because x is negative, absolute value of x is minus x, so minus of minus x is going to give you x itself, right? And because x is negative, any negative number will always be strictly less than the absolute value of x, which is always non-negative. So this then also, you can see it matches partly with the original property that we are trying to talk about. Here I've actually, in doing this proof, we have followed this trick. We have actually taken the cue from the original property that we have to prove, and we're just trying to follow through logic what will happen when we start with minus of mod x, and then we've gone on to do the proof. So that's just I'm just telling you that to give you a cue as to how you would go about doing such a proof. Anyway, so the point here is whether you look at the result numbered 1 or the result numbered 2, both together prove that this given property that I've shaded in orange above is going to be true. Right, so this is property 3, and anyway the point that you should remember from this property is that any number x, please look at where my cursor is pointing, any number x is always going to be less than or equal to its absolute value. Okay, the next property is something I had talked about in lecture 4, but because it's an important property, let me just revisit it. So here we have that the absolute value of x less than y, any number y which is greater than 0, is equivalent to writing that x lies between minus y and y. So if we have any number y which is positive, then mod of x less than y is equivalent to saying that x lies between minus y and y. Let us look at the proof here. Again, we'll bifurcate our proof into two parts, one where x is greater than or equal to 0 and the other where x is negative. So let us first suppose that x is greater than or equal to 0. Then what will happen? This inequality, modulus of x is less than y, will become x, the left hand side will become x because mod of x is equal to x. So mod of x is equal to x, which is then less than y. Remember, this is the information that is given to us. And then what we have to derive is that x lies between minus y and y. Right. So in this case, we have x lies between, x is strictly less than y. Our second case is one where x is negative. Now, if x is negative, then the absolute value of x is going to be minus x. So here we have that the inequality mod of x less than y boils down to minus x less than y, because here mod of x is equal to minus x, which is given to be less than y. And if you remember your inequalities, if minus x is less than y, and if I multiply both sides by a minus sign, then the inequality has to be reversed. So this in turn implies that x is greater than minus y. And the two cases together imply that x will always lie between minus y and y. If we were to take a generic x. So in general, x will always lie between minus y. So you can see case 1 tells you x is less than y, case 2 tells you x is greater than minus y, and combining the two cases gives you the result. Okay, now we come to what is known as the triangle inequality. The triangle inequality says that the absolute value of the sum of two numbers x and y will always be less than or equal to the absolute value of x plus the absolute value of y. In fact, this is sort of related to the idea of the triangle. It's called the triangle inequality because when you look at the triangle, you have any triangle with a positive area, you always have that the sum of any two sides is greater than the third side. So in that sense, when you apply the same idea to absolute values, you get this kind of a result which we are calling the triangle inequality. And you can see here that if we take let's say two numbers, suppose x is equal to 3 and y is equal to -4, you can check for yourself what the two sides of this inequality will be. So you can see here the absolute value of x plus y, because x plus y here is -1. So the absolute value of x plus y will be the absolute value of -1, which is equal to 1. And the right part is absolute value of x plus absolute value of y, which is nothing but 3 plus 4, because the absolute value of y is 4, and that is equal to 7. And you can clearly see here that the absolute value of x plus y, 1, which is going to be strictly less than the absolute value of x plus the absolute value of y. Let's take another example. Here we have a situation where x and y sum up to 0. So if I take the absolute value of x plus y, that is going to be the absolute value of 0, which is 0 itself. And if I look at the absolute value of x plus the absolute value of y, that is going to be 4 plus 4, which is 8. And here again you can see that we have that the absolute value of x plus y is strictly less than the absolute value of x plus the absolute value of y. Let's prove this inequality, and the idea behind the proof is that what I'm going to prove, if you just look at this ultimate result that I have, I'm going to prove that the mod of x plus y square, the square of the mod of x plus y, is equal to the square of mod x plus mod y. And if I get this result, then all I have to do is take the positive square root on both sides, and I will get my triangle inequality. Right, so let's just prove this. Now, if I look at the square of the modulus of x plus y, this is going to be equal to x plus y the whole square, because I have that the square root of x square, if you go back to the first definition, please look at this first property. The absolute value of x is equal to the square root of x square. So if I square both sides, then the square of the absolute value of x is equal to x square, right? So similarly, if instead of x I have x plus y within the absolute value symbol, which is what I have here, then the square of the absolute value of x plus y is equal to x plus y the whole square. And we know that x plus y the whole square is equal to x square plus y square plus twice x times y. And this then is equal to mod of x square. Please remember that mod of x square is nothing but x square, because mod of x is always going to be something positive. So that's always going to be the same as x square. Similarly, y square is the same as writing it as mod of y square plus 2 times xy. And now we're going to use the property number 3 that I just talked to you about, that because any number is always less than or equal to its mod, we have here that because 2 times xy, remember we have to get rid of this xy and we have to convert it into a mod, and that is something which we can do because we know that this number 2 times xy is always going to be less than or equal to the mod of 2 times xy or 2 times mod of xy. So this expression mod of x square plus the square of mod y plus 2 times x times y is going to be less than or equal to the square of mod x plus the square of mod y plus 2 times mod of x times y. Okay, so this then becomes mod of x plus because if we go by the second property, the absolute value of x times y is the same as the absolute value of x times the absolute value of y. So this expression now becomes the square of mod x plus the square of the absolute value of y plus twice the absolute value of x times the absolute value of y, which then you can use your algebra, knowledge of algebra. This expression you can see is then equal to the absolute value of x plus the absolute value of y, the whole square. So note here that we have used some very key properties for deriving this result, the triangle inequality result. We first use the first definition here, which is mod of x is square root of x square, or any number x can be written as mod of x is equal to square root of x square. So x square is going to be equal to the square of the mod. So that's the first property that we use in this part, excuse me. And then we use the fact that the square of the mod of any number is the square of x itself. X can be negative also, but once you take the square, you will get a positive. That's the second property that we use. And then we use the property where any number xy is going to be less than or equal to the mod of xy, because remember, we have to somehow bring in the less than or equal to sign. Otherwise, we were just working with equations here. And ultimately, we get this result that the square of the mod of x plus y is equal to mod of x plus mod of y, the whole square. The square of mod of x plus y is less than or equal to mod of x plus mod of y, the whole square, and then taking the positive square root on both sides will give you the desired result. Now we can also extend the triangle inequality to x minus y. So we have here that the absolute value of x minus y is greater than or equal to, here the sign gets reversed, is greater than or equal to the absolute value of x minus the absolute value of y. Now, one way of proving this is to actually do it just the same way I proved the triangle inequality, except that now you'll have minus 2xy, and that will then become greater than or equal to minus 2 times mod xy. So the proof will otherwise remain the same, except that the direction of the inequality will get reversed and there will be a minus sign there. But another way to do it is, because we've already proven the triangle inequality, let's look at the triangle inequality for any two real numbers, a and b. So we have that mod of a plus b is going to be less than or equal to absolute value of a plus the absolute value of b. Now do this, put a equal to x minus y and put b equal to y. So here you will get a plus b becomes x minus y plus y, which is then going to be less than or equal to, by the triangle inequality, a mod of a, which is mod of x minus y plus mod of y. And now you can see that this simplifies to mod of x on the left hand side of the inequality, because the y's get cancelled. So mod of x is less than or equal to mod of x minus y plus mod of y, and this then implies that we have the desired result, that the absolute value of x minus y is going to be greater than or equal to the absolute value of x minus the absolute value of y. Okay, now this is another important property, slightly tricky, but it's all right. You just pay attention here. We have here that the absolute value of x minus y is greater than or equal to the absolute value of the mod of x minus the mod of y. Okay. Now, to prove this, what we're going to do is, I'm going to write this property as the absolute value of the difference between the two absolute values of x and y respectively, less than or equal to the absolute value of x minus y. Now, to prove this part, so basically we're going to prove the property in this form. Now remember that we have this property that whenever the mod of any number t is less than or equal to a, that means t lies between minus a and a. Now think of this a here, the number a, as mod of x minus y, and think of t, the number t which is contained within the absolute value symbol, as mod of x minus mod of y. So if I apply this understanding to what I need to prove, then basically I have to prove that the mod of x minus the mod of y lies between minus of mod x minus y and mod of x minus y. Remember that my t here is mod of x minus mod of y, and a here is mod of x minus y. That is like my number, and the mod of t has to be less than or equal to a. So, I am just writing things in this format. T lies between minus a and a. So, this is what I ultimately have to prove. Now, the right part of the inequality is something we have already proven on the previous slide, right? The mod of x minus mod of y is less than or equal to mod of x minus y. What we have to prove is that minus of mod of x minus y is less than or equal to mod of x minus mod of y. Now, note here that the absolute value of x minus y is the same as the absolute value of y minus x, because both are going to be positive, non-negative. It does not matter how you write things inside the absolute value symbol. So, the absolute value of x minus y is equal to the absolute value of y minus x, and we have just proven that the absolute value of y minus x is going to be greater than or equal to absolute value of y minus the absolute value of x. Now, just use the property of transitivity. If I have absolute value of x minus y is equal to absolute value of y minus x is greater than or equal to mod y minus mod x, this is the same thing as saying this then implies that the absolute value of x minus y by transitivity is greater than or equal to the absolute value of y minus the absolute value of x. And because absolute value of y minus absolute value of x is the same as minus of absolute value of x minus absolute value of y, so our expression now becomes absolute value of x minus y is greater than or equal to minus of absolute value of x minus absolute value of y. Now, just multiply by a minus on both sides and you will get your result. So, you will have to reverse the inequality, of course. So, now you get minus of the absolute value of x minus y becomes less than or equal to the absolute value of x minus the absolute value of y, and therefore, we have proven both parts of the inequality, and that then proves the property number 7. Okay, so in the time that we have left, let me walk you through some examples relating to absolute values. This is a question that we gave in one of the Delhi University exams. It's also a popular question that you do in that students do in school. But what I normally see is that students they know how to draw the result, but they don't really understand the details behind the result. So here the question is, draw the graph of the absolute value of x plus the absolute value of y equal to 10. So our equation here is absolute value of x plus absolute value of y is equal to 10. Now, because of the way we define absolute values, this equation, if we have to draw the graph for this equation, this would mean that we'll have to take into account 4 possible cases. One, where both x and y are non-negative. So, if x is greater than or equal to 0 and y is also greater than or equal to 0, our equation will boil down to x plus y is equal to 10. Now, if x is greater than or equal to 0 but y is negative, then our equation becomes x minus y is equal to 10. Our third case is one where x is negative but y is greater than or equal to 0. So, here since x is negative, the absolute value of x would be minus x, but the absolute value of y would still be y. So, our equation will become minus x plus y is equal to 10. And our final possibility is where both x and y are negative, so that when you take the absolute value of x or y, that will be minus x and minus y, so that our equation becomes minus x minus y is equal to 10. So, please look here, we are going to draw these equations, but these equations we will draw for these particular combinations of x and y. Okay, let us look at the first case. The first case is one where both x and y are non-negative, so that our equation is x plus y equal to 10. Now, if you were to plot this graph x plus y equal to 10, you will basically get this line here, which, if you draw the complete thing, then you will be having both the blue and the red portions. So, this is y equal to 10 minus x, this entire line extending in both directions. But because by assumption here, your x and y have to be non-negative, which is to say that you are in the first quadrant. That means you will take only that portion of the line 10 minus x that is in the first quadrant. So, remember, this blue portion of the line is what you are going to take for your graph for the line x plus y is equal to 10, and this would be a part of your final answer. So, keep this in mind, the first quadrant portion, and then let's move on to the second case. The second case is a case where y is negative, but x continues to be non-negative, which is to say that you are now in the fourth quadrant. Our line is x minus y is equal to 10, which you can plot. But now you're going to take only that portion of the line which is in the fourth quadrant, which is this portion that I've shown you in blue. Is that right? So, this is how you have to pick up the portions of the lines that are relevant, that are consistent with your assumptions. Okay, our third graph here, our third case here is where x is negative, but y is greater than or equal to 0, which is to say that you are now in the second quadrant. Now, if x is negative, then the absolute value of x is minus x. So, our equation becomes minus x plus y is equal to 10, and this is the line y is equal to 10 plus x, right? So, you see it here, and now we are going to take only that portion of the line, this portion in blue, which is in the second quadrant, because by assumption x is negative and y has to be non-negative. Okay, the fourth case and our final case, x and y are both negative, which is to say our line is minus x minus y is equal to 10, and that then gives us, because now remember we are in the third quadrant where x and y are both negative. So, we will take only this blue portion here of the straight line y equal to minus 10 minus x that we have plotted, and that will be part of our final answer. So, remember we have done these 4 cases, and now let us put the 4 cases together, and this is the graph that you get for absolute value of x plus the absolute value of y is equal to 10, and I think it's a pretty nice cool looking graph. So, basically we've just put together all the 4 pieces of information from the 4 cases. So, case 1 was giving you this part of that rhombus kind of figure. So, quadrant 1, then this is the fourth quadrant, this is the second quadrant, and this is the third quadrant. So, this is our final graph, mod of x plus mod of y equal to 10. Okay, let's look at another graph. This is asking you to draw the graph of the absolute value of y equal to the absolute value of x minus 10. So, this is slightly different from what we've just done, and maybe you can do this on your own. I'll just walk you through the cases and give you the final result, but try and take up each case on your own, draw the complete line and within the space that you have on your graph paper, and then just pick out those portions which are consistent with your assumption. So, in this case also we will have 4 cases, the first one being where both x and y are non-negative. So, that would mean that the absolute value of x and absolute value of y would be x and y respectively, and your equation will then become y is equal to x minus 10. The second case is where x is non-negative but y is negative. So, that means your absolute value of y will be negative, which is to say your equation becomes minus y is equal to x minus 10. Absolute value of x is going to be x only here because x is non-negative. So, our equation ultimately becomes y. What you're going to plot is going to be the equation of y is equal to 10 minus x. I just moved terms. So, I brought y to the right hand side and x minus 10 to the left. So, I'm in this equation. So, that gives me the equation y is equal to 10 minus x. Right, the third case is where x is negative and y is greater than or equal to 0, and that in turn will give me the equation y is equal to minus x minus 10, because now mod of x is equal to minus x. And finally, the fourth case is where both x and y are negative. So this then would give you the equation minus y is equal to minus x minus 10. And again, just moving terms a little bit, this then boils down to plotting the graph of y is equal to x plus 10. I just find it more comfortable to read things this way. Otherwise, you can straight away draw the graph of minus y is equal to minus x minus 10 also, it doesn't matter. Right, so do practice these 4 cases and see what you get, and just match your answer with this. This is what you should get for the graph of the absolute value of y equal to the absolute value of x minus 10. Again, it's a nice, not the usual kind of graph. So these are interesting graphs and constitute interesting exercises. So you must practice this one also. Okay, so let's, in the last part, let me just make a little bit of a clarification about square roots, because this is something which we were asked about on email, because if you remember the definition that I gave you for the absolute value, let me go back to the first property. It's saying the absolute value of x is the square root of x square. Basically, this is a discussion I brought in the 4th lecture also, where I said, suppose I ask you what is the square root of 9, and here the answer is that the square root of 9 is plus 3, not plus minus 3, and basically that is where your definition is really taking you, because if you were to say square root of x square is plus minus x, then you will not get mod of x, because mod of x is always going to be something non-negative. So you can't have a negative number as a square root of x square. But let me give you a little bit of a clarification about square roots, which I have picked up from a book only, so you can be rest assured I'm not making it up. So this is from the textbook by Binmore, and let me just clarify a little bit about square roots here. Let us suppose we have a number y which is greater than or equal to 0, whose square root we want to take. So like we were talking about 9, so y would be 9. Now by definition, the value of x greater than or equal to 0 that satisfies the equation y equal to x square is called the square root of 9. So basically, if we have the equation y is equal to x square or x square is equal to y, whichever way you want to look at it, then the value of x, the non-negative value of x, please remember here, this is the convention, the value of x has to be greater than or equal to 0, and that non-negative value of x which satisfies this equation y is equal to x square is called the square root of y. Now, if I simplify this equation y equal to x square, obviously I'll get 2 numbers for x, but because we are restricting x to be greater than or equal to 0, so I have x is equal to the square root of y, which is how we write the square root, the symbol. And with this convention, because we have by definition x has to be greater than or equal to 0, we have that the square root of y is always going to be greater than or equal to 0. Let's just put in some numbers and see that this indeed is how things work out, because otherwise you probably may not understand with just x's and y's. So let's suppose our y is 9, that's what we were talking about. Then the square root of 9 is that value of x, remember that value of x greater than or equal to 0, that satisfies the equation x square is equal to 9, and that value of x which is non-negative, which will satisfy this equation, will be nothing but 3. Now obviously there are 2 numbers that satisfy this equation x square equal to 9, which is plus 3 and minus 3, but remember that we are defining the square root by convention as x being greater than or equal to 0. So we're going to have that the square root of 9 is 3. Let's just get a sense of things in general also. So when I look at the equation x square is equal to y, there are obviously 2 numbers. So just as we were talking about x square equal to 9, if in general I look at the equation x square is equal to y, there are obviously 2 numbers whose square is y, right? So you can also see it here. When I solve this equation x square equal to y and I take y to the left hand side, I get x square minus y is equal to 0. And now you can also write this as x minus square root of y times x plus square root of y is equal to 0. So that in turn implies that x is equal to the square root of y, or x is equal to minus of square root of y. So x is either the positive square root of y, or x is equal to minus the square root of y. But remember, the square root of y, so there are two numbers that satisfy the equation x square is equal to y, which is plus square root of y or minus square root of y. But that square root of y, which I have put in circles here, that itself always has to be greater than or equal to 0. You can't put a negative number. So when suppose y is equal to 9, then when I solve the equation, I'll get x is equal to 3 or x is equal to minus 3, but that minus 3 is, this minus is outside. Square root of 9 is always 3. So I hope this makes sense, and with this we reach the end of today's lecture, which was about absolute values, and with this I also complete my discussion of absolute values, except when we discuss shifting of graphs, I'll bring in some absolute value function graphs again. But that's it for today. In the next lecture, we will be talking about quadratic functions, and maybe I'll also talk about some examples from circles, even though circles are not functions, but since I touched upon the idea of a circle in my previous lecture, let me walk you through some examples relating to the circle. So that's it from me for today. Bye-bye. Take care. Geetika.
Thank you so much for giving us this session. Friends, you are requested to write to us at info.cec@nic.in for your queries as well as for your feedbacks. We are taking your leave with the promise that we are going to meet again soon. Till then, take care. Goodbye. Thank you.
Thank you, Geetika.